Hi guys! In this video we're going to be looking at principle of moments example, finding centre of mass of an irregular rod, and we're going to finish with a summary.
So first of all, we need to discuss what the principle of moments actually is. We know that for an object to have no translational acceleration, all forces must be balanced. So for example here, we have one hand exerting a force on this pencil and another hand exerting a force on this pencil in the opposite direction. And if these forces are of equal magnitude, the resultant force is going to be equal to F minus F, which is 0. So there is 0 resultant force, so we can therefore say that the acceleration is going to be 0. So there's no translational motion. However, this still leaves the possibility of a rotation due to unbalanced moments. So these two forces still create a net moment. So there'll still be rotational motion. So the pencil will experience a rotation. However, we can also have the case where the turning effects of the forces cancel out instead. So now let's imagine the person is applying both forces from the top of the pencil, like this, and they're both of equal magnitude still. So although now we do get a translational acceleration, there's no turning effect. So the net moment is 0 because the clockwise and anti-clockwise moments cancel, so there's no rotation. Each of these forces would have a turning effect individually, but together they have none. So if we were to apply each force on its own, we would get a turning effect. So for example, if we apply the force on the end of the pencil here, on its own we do get a turning effect. So the pencil would move anti-clockwise. And likewise, if we were to apply the force on the other end of the pencil, we would again get a turning effect. However, this time it would be clockwise. So if we recall that clockwise moments add with clockwise moments and cancel with anti-clockwise moments, so we can understand here why in this case, where the forces are applied above the pencil, why we get no turning effect, and why in this case we do get a turning effect, so when they're applied in opposite directions. So we can see from the force on the left we get anti-clockwise moment M1, and from the force on the right we get a clockwise moment, which we're going to call M2. So from the principle of moments we can say that the anti-clockwise moments are equal to M1 because that's acting anti-clockwise minus M2 because that is acting clockwise. And now if we look at the other case where the forces are acting in opposite directions, we can see that M1 is still acting anti-clockwise, but M2 is now also acting anti-clockwise. So now if we add together the anti-clockwise moments, we get M1 plus M2. So we can see there's a difference here depending in which direction you apply the force. So this means that in the case of where the clockwise moments equal the anti-clockwise moments, they cancel entirely. So in the situation where we're applying the force from above and we get an anti-clockwise moment M1 and a clockwise moment M2, when we add together the anti-clockwise moments and we get M1 minus M2, if M1 is equal to M2, then the two moments are going to cancel. So the total anti-clockwise moment is going to be equal to M1 minus M1 because it's got the same magnitude as M2. So this gives us a resultant moment of 0. And if there is no overall moment, there cannot be an overall turning effect. So the pencil will not rotate. There will be no rotational motion. This gives us our condition for there to be no rotation in the system, and this is called the principle of moments. The principle of moments states that for an object to be in equilibrium, the sum of clockwise moments about any point must be equal to the sum of anti-clockwise moments about that same point. So we saw in our earlier example, in this case, if the two forces here have the same magnitude and they are applied at the same distance away from the centre of rotation, the anti-clockwise moments will equal the clockwise moment, so there will be no rotational motion of the pencil. So let's apply the principle of moments to an example. We can use the principle of moments to find unknown quantities in situations where forces have no overall turning effect. So we can use the principle of moments in situations where a system is in equilibrium. So for example here, this mass will exert a weight W1 on the rod, and this mass will exert a weight W2 on the rod. And we've also got the rod's weight acting on it, and we've also got a normal contact force here from the pivot. So an example of this would be masses balanced on a rod which is also on a balance, and that's what we've got here. So if there is no turning effect, this allows us to find unknown quantities. So let's look at an example. If we place a 10 kilogram mass on a uniform rod on a balance 0.5 meters away from the center of the rod, where must we put a mass of 5 kilograms in order to keep the rod from turning? So where must we place the mass in order for the system to be in equilibrium? So step 1 is to draw a free body diagram for the rod. So we know that we've got a 10 kilogram mass here. So this mass will have a weight of 10 kilograms times the gravitational acceleration of the Earth. And we know that this mass will exert a clockwise moment. So we've got a clockwise moment from that mass. And this mass is a distance 0.5 meters away from the center of the rod. So here, that is 0.5 meters. And now we've got this other mass here, which has a weight equal to 5 kilograms times g. And this mass is going to create an anti-clockwise moment. And we want to know where we're going to place this mass on the rod in order for the rod to be in equilibrium. So we want to find this distance x. And let's not forget, we've also got the weight of the rod, and we also have the normal contact force from the pivot, which is r. So now our next step is to write the equation for the moment of a force. So we know that a moment of a force is going to be equal to that force multiplied by the perpendicular distance of the line of action of that force from the point at which we're taking moments about. Now our third step is to make a careful choice of where we take moments from to neglect the weight of the rod, because we don't actually know what the weight of the rod is. So we don't want to be doing any calculations that involve this quantity. So we know that we have a uniform rod. So this means that the centre of mass is at the centre of the rod. So we're going to take moments about the centre of the rod in order to neglect the weight of the rod. So we can double check this. If we then were to find out the moment of the weight of the rod, we would find that it's equal to its weight multiplied by 0. Because if we're taking moments about the centre of the rod, the weight of the rod is going to act through its centre since it's uniform. So therefore the distance of the line of action of the force from the point at which we're taking moments about is going to be 0. So this gives us 0. So this gives us a moment of the weight of the rod which is equal to 0. So step 4 is to write the principle of moments. So we've just learnt that for no turning effect, the clockwise moments and the anti-clockwise moments must balance. So mathematically, we can say that the clockwise moments are going to be equal to the anti-clockwise moments acting on the system. So now we can take clockwise moments about the centre of the rod. So we know that the equation for the moment is given by force times the perpendicular distance. So the clockwise moment is going to be given by the weight, which is 10 kilograms multiplied by the gravitational acceleration, g, and then this is going to be multiplied by the perpendicular distance from the point at which we're taking moments about. So that's 0.5 meters. And if we simplify this, we get that the clockwise moment is equal to 5g, because 10 times 0.5 gives us 5, so we've got 5 kilograms times g. Our next step is to take anti-clockwise moments about the centre of the rod in terms of the unknown distance, which is x. So now the anti-clockwise moments is going to be given by 5 kilograms, because that's the mass of this mass. So we've got 5 kilograms multiplied by g, that's the weight, and then we multiply this by the unknown distance, which is x. Well, not really simplifies, but then we can rewrite this as 5g times x. So now we can equate the clockwise and anti-clockwise moments. So there's no turning effect, as we've said, which allows us to say that the clockwise moments are going to be equal to the anti-clockwise moments. So therefore, we've got 5g, that's what we found our clockwise moments to be, and this is going to be equal to 5g times x. So now all we have to do is to rearrange our expression for x. So we've said that we've got 5g is equal to 5gx. So now to find out what x is, we just have to divide 5g by 5g. So we get 5g divided by 5g, and this gives us a value for x, which is 1 meter. So that is where we need to place our mass in order for the moments to balance. So finally, we're going to use the principle of moments in order to find the centre of mass of an irregular rod. So far, we have dealt with problems involving a uniform rod, where the centre of mass is at the centre of the rod. So here we have a uniform rod, and we've always said that the weight acts at the centre of mass, which is in the middle of the rod. So over here is our centre of mass. And this has allowed us to neglect the weight of the rod and the reaction force by taking moments about the centre of the rod, because that's where the weight and also the reaction force from the balance are acting. However, it's possible to have an irregular rod where the centre of mass is somewhere apart from the centre. So for example here, the centre of mass might be at this point, so the weight is going to act here. So now this is where our centre of mass is. So we can see that it is a distance x away from where the balance makes contact with the rod, but the normal reaction force is still going to act at that point. This means there will be a net moment and the rod will tilt towards the side with the centre of mass. So we can no longer balance the rod on a pivot like we could before. We can apply the principle of moments to help us find the centre of mass of the irregular rod. So to do this, we investigate how the moment of a mass's weight balances about a point on the rod. So we've said here that the centre of mass of the rod is acting at this point. So we have the weight of the rod and we know this. But we want to know the distance at which the centre of mass acts from the centre of the rod. And we're also going to use a mass of known weight And we're going to measure the distance away from the centre of the rod at which there's no turning effect. Because at this point, the clockwise moments and the anti-clockwise moments will balance and the system will be in equilibrium. So let's apply this to an example. A 10 kilogram rod is placed with the support at the centre and a 2 kilogram mass at a point 4 meters from the centre. How far is the centre of mass from the centre of the rod if the rod is not turning? So if the rod is not turning, we know it's in equilibrium. So our first step is to draw a free body diagram. So this is going to look similar to the one we've just done, but now we've got some known values. So we've got the weight of this mass, and that is going to be equal to its mass, which is 2 kilograms, multiplied by g. And then we've also got the weight of the rod, which is going to act at a point here. And this is going to be equal to its mass, which is 10 kilograms, multiplied by g. So we know that this mass has been placed a distance of 4 meters from the pivot. However, we don't know at what distance the centre of mass acts, and this is what we want to find out. And we've still got a reaction force from the pivot. So our second step is to write the equation for the moment of a force. So we know that the moment of a force is given by the force multiplied by the perpendicular distance of the line of action of the force from the pivot. Step 3 is to make a careful choice of where we take moments about. In this case, we can make the problem easier by taking moments about the centre, so we do not have to calculate the reaction force. So if we take moments about the centre, the moment due to the reaction force is going to be given by the magnitude of the reaction force times 0, because the reaction force acts through the centre. So the perpendicular distance is 0. So we therefore get a moment which is equal to 0 Newton meters. So this allows us to ignore the normal reaction force. Step 4 is to write the principle of moments. So we've got no turning effect. And this therefore means that the clockwise moments are going to equal the anti-clockwise moments. Now we're going to take clockwise moments about the centre of the rod in terms of the unknown distance x. So the clockwise moments are going to be given by 10 kilograms, which is the mass of the rod, multiplied by g. So this is the weight of the rod. And now we need to multiply it by our unknown distance x, which is what we're looking for. So this gives us the clockwise moment acting on the rod. And we can also take anti-clockwise moments about the centre of the rod. So the anti-clockwise moment is going to be given by 2 kilograms times g, which is the weight of the mass, because it's the mass that's creating an anti-clockwise moment on the rod. And we're going to multiply it by its distance from the centre, which is 4 meters. So we can simplify this to say that the anti-clockwise moment is given by 8 times g. And now our final step is to equate the clockwise and anti-clockwise moments. So we are saying that the clockwise moments are equal to the anti-clockwise moments. And therefore, we can say that 10 times g times x is equal to 8g. So we can see here that the g's are going to cancel. So now we're left with an expression for x. And this takes us on to our last step, which is to rearrange to find our distance x to the centre of mass from the centre of the rod. So we've got the expression that 10x is equal to 8. So now to find x, we simply have to divide 8 by 10. And this gives us a value of x, which is 0.8 meters.
Hey guys, I hope you enjoyed the video. If you're looking for an amazing A-level physics resource, join me today in my series of engaging bite-sized video tutorials. Just click the SnapRevise smiley face and together let's make A-level physics a walk in the park.